Back, everyone. I hope the practicals worked. It's not so easy in the virtual environment. And now I hope you're all ready to listen to the next part of the lectures. I'm very happy to introduce Elia, who will present her lecture on discovering the ionosphere and the magnetosphere. And you're welcome to make a 5-minute break in the middle of your lecture whenever you like. Okay, so please go ahead.
Okay, thank you, Monica. It's a pleasure to be here, to be part of this school, to have this opportunity and attend this invitation. And let me share my screen here and we get started. Okay, do you see it in presentation mode now?
Yes, it works.
All right. So, the title of the talk is Discovering the Magnetosphere and the Ionosphere. I am a scientist from the National Institute for Space Research in Brazil. The idea is to give a tutorial, so very general, a broad overview of the main characteristics of the magnetosphere and the ionosphere, some of the coupling that happens between them and with the neutral atmosphere, and to discuss a little bit how energy comes down from space via the solar wind and create these regions. And I will just tease you about how this energy, when it gets down to the surface, starts coming back up out to space and also creates some interesting plasma and energetic particles, and is a new component of the system and the space weather. And that will be the subject of my talk on Thursday. So I hope you all get interested by what I'm going to say today and come back on Thursday to see the rest of it. So everything starts with the sun. The sun is the main driver of our solar system and of life on the surface of the Earth. The plants, the animals, us human beings. So it's the main source of energy for all processes on our planet. And here we have a very nice movie showing the sun with some activity and a very nice solar flare. So the sun regularly emits part of its matter to space via what we call the solar wind. And every so often it has these explosions that we call flares, and we have coronal mass ejections, all sorts of features happening with the sun that directly affect not just Earth, but all the planets in the solar system. The interplanetary magnetic field and the solar wind interact with the magnetic field of all planets in the solar system and creates a cavity that we call magnetosphere. So here we see a picture of the sun and a representation on the magnetic field lines, how it gets frozen to the plasma and gets carried as the sun rotates. So to have an idea of scale, here is Mercury, Venus, and we are here on the Earth. And this structure creates a current sheet that has this beautiful shape that we call the ballerina model of the sun interplanetary current sheet. And again, the Earth is here. I cannot find my mouse. Anyway, here we are. And to have an idea of the scale, Jupiter is here. So as the energy gets down towards the surface of the planet, it is the main source of the ionized regions along the way, which are magnetosphere. And within the magnetosphere, we have the radiation belts, the ionosphere, which is also a plasma region, much closer to the surface. And it's also responsible for the atmospheric conductivity, which is within the neutral atmosphere, which is where we live. So here we have a completely out of scale representation, but a beautiful image of the sun emitting some solar matter towards us. And this is Earth, and this is the magnetic field and how it gets compressed by this solar wind coming towards our direction. And again, as this energy reaches the surface, it is partially reflected upwards, making its way back to space. And this infrared radiation that is emitted by the surface of the Earth when it's heated by the sun radiation, it creates thunderstorms when there is moist air around, and thunderstorms have electric charge, so they have currents, which are the lightning discharges, and therefore they also create plasmas and energetic particle emissions like gamma rays, X-rays, and many interesting and relatively recently discovered phenomena. But the solar wind's not going to do anything if our planet doesn't have a magnetic field. So let's see some general characteristics of Earth. So the equatorial diameter is 12.750 kilometers. It's within an average distance from the sun of 150 million kilometers. The average age of the planet is between 4.5 and 5 billion years. Its mass is around 6 times 10 to the 24th kilograms. The gravity acceleration is 9.78 meters per second square. The rotation is 1 day, and of course, we are measuring within our own units. And we call one rotation of the duration of our planet's rotation a day. And the translation is the same thing, it's 1 year. We know one satellite, natural satellite, which we call the moon, and the temperature goes from minus 70 degrees Celsius to plus 50 degrees Celsius. And now with the changes we're having in climate, we know that it can get higher than that. The main atmospheric constituents of our neutral atmosphere and also our ionized region are nitrogen and oxygen. Within the planet is where the main magnetic field is created. So for our understanding, we make this division that you see here. So the outer region, which is the region where we live, we call crust. And then the first inner region, which is fluid, we call mantle. And then within the mantle, we have a more fluid and denser region that we call core. Some people call it the outer core. And within that, we have an inner core that we believe is a solid. It's a crystal made mainly by iron, 80%, and a little bit of nickel. And the current measurements and models converge to having a solid inner core within the Earth. Now, the magnetic field is generated by currents that are flowing within this core region, the outer core region, and they create a dipole field, which is represented here. It's an inverted dipole, so the north pole of the magnetic field points towards the south of the planet. Therefore, the magnetic field lines point upwards. And it's tilted by about 11.5 degrees from the geographic poles. The field is such, the currents are such that it creates a magnetic field of about 0.5 Gauss on the surface. And this is one of the largest magnetic fields of the telluric planets that we have in the solar system. Now, these currents, they're not homogeneous, nor necessarily symmetric. So they create a magnetic field that has different intensities throughout the surface of the planet. And this is what you're seeing here. the intensity here given in nanotesla. And that's a simulation from Finland et al. It's a very recent paper from last year. And they see, the most important thing that they see is that this region here that's been known for a long time, it's called the South Atlantic Magnetic Anomaly, is actually increasing its intensity. So before we didn't have this minimum here. We only had one minimum, and now we have two minima in the anomaly. Now, this is a fairly important region because since the magnetic field is weaker, so the particles that are drifting, energetic particles, electrons and positive ions and protons and others, they come closer to the surface of the Earth, so they get more in contact with the neutral atmosphere and they get lost. They stop their drift movement that I will talk a little bit more in detail later. And so they create further ionization in the top of the neutral atmosphere. There is some change in the conductivity. And the most important thing at the moment is that we have scientific satellites that have polar orbit, or not quite polar, but they have a low orbit that go across this region. And these satellites, they end up turning off their equipment when they fly over South America or this region in the South Atlantic Ocean, to avoid damaging their instrumentation due to the high flux of energetic particles in this region. So we don't have a lot of good scientific data on the ground here in South America, nor in this region in the Southern Atlantic Ocean. So with this interaction of the solar wind with the Earth's magnetic field, we have what we call the magnetosphere. And as you see, it's a very complex structure. This is a beautiful picture showing the main features of the magnetosphere. And the first one that we call your attention for is the bow shock region, which is this region here. And this is where there's the first impact of the solar wind with the Earth's magnetic field, and it creates this shock region. It's where the solar wind abruptly slows down and start flowing along the field lines here, deflected from the magnetosphere. It's located at about 90,000 kilometers altitude from the Earth, and it has about 17 kilometers of thickness. So it's a fairly thin region. Right after the bow shock, there is what we call magnetosheet, which is a region of transition between the shock, the solar wind, and the magnetosphere itself. And it's a very turbulent region with different currents and very dynamic plasma in that region. Then the next feature is the magnetopause, and that defines where the magnetosphere starts. The magnetopause is about 10 Earth radius of that distance, 10 Earth radii distance from the surface, which is 63,710 kilometers altitude. Then we have the magnetosphere, which is a region, the definition is a region where the movement of the particles is defined by the magnetic field, in this case, the magnetic field of the Earth. It has a very complex structure of currents. You can see some of them here, a cross-tail current. You can see field-aligned currents. You can see the magnetopause current. And it has a very important function for living organisms on the surface of the planet, because it protects the biosphere from direct interaction with the solar and cosmic radiation. Some of it get in via the cusps here, the regions where the field lines point toward the ground, but it's slowly, strongly reduces the penetration of the solar wind. And it also has an impact reducing atmospheric erosion due to the solar wind. So the neutral atmosphere would get quickly lost if there was a direct interaction with the solar wind. So the magnetosphere also protects the neutral atmosphere. It's very far close to the ground into the system, but still is an important effect of protecting it. And the interaction between the solar wind and the magnetosphere creates space weather. And as we'll see along the way, there are some new components now that it's also a result of the solar energy, but as I mentioned, coming from below and making its way back out to space. The next feature I want to talk about are the radiation belts. So both the magnetosphere and the radiation belts were discovered in 1958, and they are called Van Allen belts because Van Allen was the scientist who discovered them. He used the satellite Explorer 1, which was the first artificial satellite from the United States, and the second satellite, artificial satellite from Earth. So here is what we know nowadays of the structure of the radiation belts. There is an outer belt that you see here, many layers, and an inner belt that you see here. The inner belt is about 1,600 kilometers altitude to more or less 12,900 kilometers. For you to have an idea of how far that is, a low orbit satellite, for example, the International Space Station, is only at 370 kilometers altitude from the Earth. So they are really, really far into space. You can also see that a geosynchronous satellite is, for example, around 400 kilometers altitude. So this gives you an idea of scale of those satellite positions and the radiation belts. So the idea that a cavity is formed when the magnetic field of the Earth diverges the solar wind was first proposed by Chapman and Ferraro. This happened in 1931. And then later on, the satellites Explorer 10 and 12 confirmed their ideas. The first thing that happens is that we have the bow shock, as I mentioned, because the solar wind travels at about 400 kilometers per second, and that speed is supersonic. The fastest plasma waves travel between 50 and 100 kilometers per second, so the solar wind is traveling much faster than fast plasma waves, so it creates this shock region. Just like a supersonic airplane creates a shock region in front of it, because it's traveling faster than the speed of sound on air. So it forms the bow shock region, and the bow shock has a function of slowing down, compressing, and heating the solar wind plasma. Then with that, the magnetosheet is created. It's not a supersonic plasma, but it's turbulence, and its speed increases as it moves around towards the tail of the magnetosphere. And the magnetopause is located where the solar wind pressure is equal to the magnetic field pressure of the Earth's magnetic field. And we can calculate that by equating the two pressures. So this is the solar wind pressure. This is the pressure of the magnetic field. And this, we can rewrite this equation this way. So now here we start seeing it as a function of the distance. And in this equation, so the rho is the density, and V is the velocity of the solar wind, B is the field, and the field is given by this expression where B is the magnetic dipole momentum. So we solve this equation for the radius, and then we have the average magnetopause distance as 10 Earth radii, as I have mentioned before. So the magnetosphere plasma is composed by solar wind plasma mainly, and some ionospheric plasma. The ionosphere is created by ionization of a neutral atmosphere by solar radiation, and during the night is maintained by chemical reactions. It has a very complex structure of currents, the magnetosphere, and the currents, they transport charge, mass, momentum, energy, and they create magnetic fields that modify the pre-existing fields. The main currents in the magnetosphere are the Chapman-Ferraro current, the magnetopause magnetotail current, field-aligned currents that are called Birkeland currents because he was the one who first proposed them, the ring current that connects the magnetosphere and ionosphere and drives magnetic storms, substorms, a lot of space weather phenomena, and the Bow-Shock current. As the magnetosphere responds to changes in the solar activity, there are other currents that are created that are of short duration. So these are the main currents, and I will briefly explain what each one of them is. So first one, the Chapman-Ferraro current, is created by the compression of the magnetic field on the day side due to the solar wind kinetic pressure, and that creates the current. If the solar wind pressure increases, the magnetopause gets squeezed and gets closer to the Earth. So an example for you to have an idea, if the solar wind pressure is 10 times higher than it normally is, the distance of the magnetopause goes down, it gets much closer to the Earth. Instead of 10 Earth radii, it becomes around 6.5 Earth radii. This current flows this way in the magnetosphere, and then it goes around the cusps. This is a weaker magnetic field region. This is also a region where the field points to the ground, so plasma can penetrate here. So this is how the Chapman-Ferraro goes, northern hemisphere, and the same thing in the southern hemisphere. So there's also the magnetotail current. There is a current that flows across the magnetotail from dawn to dusk, and the loop closes in the upper side and the downside, and then it flows again this way. So this is how the magnetotail current goes. Then in 1908, Birkeland proposed field-aligned currents to explain magnetic field variations that they were measuring on the ground in the polar region. And in 1974, a magnetometer on board the polar orbit satellite Triad confirmed that there were indeed field-aligned currents. They are very important for magnetosphere-ionosphere coupling because, as you can see here, a current flowing up across the lobe and coming down, they bring solar wind plasma to the lower atmosphere, to the ionosphere. They couple with the Pedersen currents, for example, and they have a complex relationship with Hall currents and other currents, and they create aurora. So we have two beautiful displays of aurora here. Now you understand the general lines, how the aurora is created. We also can see a beautiful image of the aurora from the space shuttle that's at 300 kilometers altitude. And aurora should occur in both hemispheres because we have field lines coming to the ground in both of them. And they indeed do. This is a nice movie showing these observations. It's not a privilege of our planet. As I mentioned, all the planets in the solar system do have magnetosphere, and they all have aurora. So this is beautiful images of aurora in Saturn and also in Jupiter. And by the way, all planets also have an ionosphere except for Mars and Venus. So the movement of charged particles in the magnetosphere is controlled by the magnetic field. So how do the particles move? So first thing is that electrons and positive ions, they gyrate in opposite direction. So they make this circular movement, we call it cyclotronic movement, in opposite directions due to the magnetic force. And from that, we can deduce the magnetic momentum and the magnetic moment. And it's a adiabatic invariant of this system. So besides gyrating around the field line, they also have a movement along the field line, and they bounce when they get closer to regions where the magnetic field is stronger because of energy conservation. So if we separate the parallel velocity parallel to the magnetic field from the perpendicular velocity, we have this equation for the kinetic energy. The energy needs to be conserved. And if we take advantage of the definition of the magnetic moment here, and we place it here, we see that the time variation of this moment has to be 0, which means it has to be constant. So what happens is that when the particles reach regions of increased magnetic field, the perpendicular velocity, it grows while the parallel velocity goes down. And if there is no initial velocity, it will reach a point where the parallel velocity will be equal to 0, perpendicular velocity will be maximum, and then the particles will feel a force and will come back along the field line in the other direction. Besides that, the ions and the electrons, they drift, and they drift in opposite directions. So this is what's shown here. Positive particles one direction, electrons another direction. Another current, which is the current that I mentioned that connects the magnetosphere and the ionosphere, is the ring current. And it's actually caused by a gradient in the plasma pressure. So here is the current density, is B cross a gradient of the pressure over B square, if we assume an isotropic plasma. It has an eastward component and a westward component, which are not 100% symmetric. So here we see the eastward component of the ring current, and the intensity is about 2 nanoamperes by meter square. And because of the pressure gradient, the pressure is maximum here in this point. So there is a gradient towards each direction. There is this current flowing in the westward direction, and that's a much stronger current than the eastward current. It's between 1 to 4 nanoamperes per meter square in quiet times, and in the disturbed times, it can go up to 50 nanoamperes by meter square. So there are many changes that happen in the ring currents when there are geomagnetic storms and substorms. It's a very important coupling current of this whole system. And the last current that I will talk about is the bow-shock current. And it happens as the solar wind it comes across the bow shock. The magnetic field of the Earth is compressed. We have a curl in the magnetic field. Curl of the magnetic field creates current. So this current produces a force on the solar wind. So it will produce a force pushing the solar wind back, and does work against the solar wind flux. And by this way, it extracts mechanical energy from the wind, generating enhanced fields and currents. So here are some simulation of this current, and it shows that it connects with the Chapman-Ferrari current. We see here and here as well. And it balances the pressure when other currents are not produced. So it's an important current of the system, not very studied yet. Very well. So we now know all the basic currents of the system, and now we can start looking how the solar wind interact with the magnetosphere. So the most important things that it does is to transfer energy and momentum to the magnetosphere, and it has two main mechanisms: merging and reconnection of the magnetic field lines, first proposed by Dungy in 1961, and the viscous interaction, which was first proposed by Exford and Hines. So here we have representations of each one of those, and we are going to look into a little bit more detail in each of them. The magnetic merging and reconnection is actually the most important one. It transfers solar wind stress across the magnetopause. It produces, the reconnection in the tail produces a lot of energetic particles, which play a major role in generating and maintaining the radiation belt. It's a self-driven process, and the plasma flux go around on the sides from the tail to the front of the magnetosphere, closing the loop. So here is a movie from NASA showing very nicely this process that I just explained here. Let's see. So we start seeing some increased activity in the sun. And we move away to get more perspective. And then the winds start arriving on the Earth, and we see how the solar wind opens, connects with the field lines and open them and bring them towards the tail of the magnetosphere. And this start compressing the field lines, they connect, and some of this flux comes into the system, creating auroras and other phenomena. So that's the main mechanism, and but the viscous interaction is also important. It also transfers a mechanical stress across the magnetopause, and what happens is this plasma in the low boundary latitude layer becomes entrained by the solar wind and start flowing to the tail, as you see here, and it circulates back towards the Earth. So, and it has circulation in the northern hemisphere and in the southern hemisphere, and it induces currents and convection patterns in the ionosphere, as you see here. So this is the main thing. It flows in the boundary layers and drags the magnetic field, also producing field-aligned Birkeland currents. So it's a complex mechanism. Magnetic storms affect the ring current. They produce a global reduction of the horizontal component of the magnetic field. And they are created by coronal mass ejections or large amplitude Alfvén waves that have high speed and have the magnetic field pointing towards the south. And so this southward pointing field connects with the field lines in the day side of the magnetosphere, and they can create magnetic storms. In 1957, an index was created to quantify how much disturbance would happen in the ring current. And this index is called Disturbance Storm Time, which is DST. Now, Gonzalez et al., colleague from INPE, is the scientist who provided a definition that is used most widely. So the definition is that the pressure-corrected index has to be less than minus 50 nanotesla. This is when we can call a magnetic, the phenomena that's happening is a magnetic storm, or superstorms that have this index less than minus 250 nanotesla. So why is all of that important? Well, because this large ring currents produce a weakening in the magnetic field at the surface. They create Joule heating in the ionosphere. They can create auroras, and they affect our technology, our satellites. They affect the communication of our satellites, because any signal from a satellite is an electromagnetic signal, and it gotta go across the ionosphere. So when it does this movement, it will be affected by the different conditions of the plasma there. Furthermore, the time variation of the magnetic field will induce currents in the ground, which will affect our power grid systems. So there is a lot of impact in our technology. Substorms also may have this impact that I mentioned, and they are very similar to magnetic storm, except that for the magnetic storm, the field, the interplanetary magnetic field, has to be southward for a long time, and in the substorm they don't. The reconnection and merging can happen and then stop for a while, and it can happen again. So these are the main differences. And substorms drive convection to the tail of the magnetosphere. The convection is adiabatic, and the pressure here grows to the point where it can't be sustained anymore, and the reconnection happens, and the plasma flows in this direction, and then like this, and creates all sorts of effects. So I just mentioned that in magnetic storm, reconnection is a quasi-steady process because of the long-lasting southward interplanetary magnetic field, which means the solar wind magnetic field. They are both driven by reconnection in the tail of the magnetosphere. And during magnetic substorms, the reconnection is episodic, and it's driven by the solar wind electric field. During storms and substorms, both, there are large currents that are induced in the ionosphere, which are called electrojets, and they produce all sorts of space weather effects that we talked about before. So here we have 3 different instances of the nice video from NASA showing the solar wind or a coronal mass ejection connecting with the field lines, opening the field lines, bringing it to the back, compressing it to the point that it reconnects, and plasma flows this direction towards the system. Excess plasma is liberated towards the tail. So here are the kind of effects that we can see. So there can be disruption in the electric grid. There are earth currents. We have currents that may flow then in the oceanic oil platforms. There is radiation that may hit people in the airplane and also on the ground, but up here the atmosphere is more rarefied, so the effect is stronger. There are instabilities that are created in the ionosphere, and we can have plasma bubbles that can affect satellite communication. There may be solar cell damage. There's the issue of the astronaut safety. So these are all from the energy coming from above. And now we know that thunderstorms that are created by this infrared radiation which is the solar radiation coming back up to space, plus humidity. We have thunderstorms, they have lightning discharges, they can excite these types of plasmas, gigantic jets, blue jets, sprites, halos, elves, which are in the bottom of the ionosphere, that are transient and will also have an impact on space weather that we are not quite sure yet what it will be. We already know that the elves, they heat up the bottom of the ionosphere and they can increase the ionospheric density locally. They change the radio wave propagation here. And we also have the gamma ray production, which is produced by the lightning discharge, by the way. It's produced down here and it propagates isotropically. But this picture is so busy that this was the best place that I found to put it, which is still okay because it comes from the cloud and it propagates isotropically like this. And here we have energetic electrons and positrons, which are antimatter. They are the equivalent of the electron with positive charge. They follow the magnetic field lines. So they get coupled all the way up to the radiation belts. And we know now they are a source of particles to the radiation belts. We don't quite know the numbers yet. It's not a major contribution, but still it is a contribution. So this was the coupling of magnetosphere, ionosphere, and neutral atmosphere. And now let's start talking a little bit more about the ionosphere. So what is the ionosphere? And I think now would be a good time to make a little 1 or 2 minutes break, as Monica suggested, before we get started with the ionosphere. So I'll just stop sharing a little bit and I'll make a quick stop.
Thank you so far. And yeah, let's continue in 5 minutes. So far, there are no questions yet in the chat or in the Slack channel for questions.
Okay, so we come back in 5 minutes then.
Let's meet again in 5 minutes. Yes, thanks.
Okay, so we're now going to start talking about the ionosphere, and it's the region in the atmosphere in which the plasma is really weakly ionized, and just playing with my windows here. The plasma is weakly ionized, but still has enough free electrons and ions such that it affects the propagation of radio waves. So that's the definition of the ionosphere. It was discovered in 1927 by E.V. Appleton, and there is an anomaly in the plasma density that carries his name. Most of the ionization is due to UV solar radiation, and it creates primarily oxygen positive atoms, oxygen positive molecules, and nitrogen. And those initial ions, they give rise to via secondary reactions and create other ions, other species. Extreme ultraviolet radiation and X-ray and cosmic ray create ionization in the ionosphere. They are very important and they vary with the solar cycle. So it's a direct coupling of this layer that's closer to us, this plasma layer that's closer to us, direct coupling with the sun activity. There is a quantity called optical depth that's defined by this equation and is a measurement on how the ionosphere or the atmosphere itself is transparent to the solar radiation. So here in this equation, N is the neutral density, H is the scale height of the atmosphere, sigma A is the absorption cross-section, and theta is the solar zenith angle. And here we see some classification according to temperature, the troposphere, the stratosphere. It's not shown here, but we have the mesosphere and then the thermosphere above it. And it shows more or less the ionized regions. The D layer is the first region starting around 50 kilometers. Then there is the E layer and then the F layer. And we have lightning discharge here. They create radio waves that get reflected eventually from the ionosphere. During the day, they get reflected in the D layer. During the night is in the E layer. And here we have within vertical scale to the figure, the transient luminous events, the blue jets, gigantic jets, halos, sprites, and elves. And here I put the gamma ray emissions and the energetic particle emissions that get connected to the field lines, magnetic field lines. Okay. It doesn't want to go to the next slide. Looks like my presentation is stuck. Oh. Okay. So the ionosphere is divided in layers. During the day, these are the layers, the D region, the E region, the E layer, and then there are sporadic E layers that can happen as well. The F region has two main layers during the day, and near the equator, the magnetic equator, a third layer called F3 was also identified in low, well, near the magnetic equator. During the night, it's a much simpler structure. It has the E layer because there is no sunlight to create this ionization. There is a lot of chemical reactions happening here. So only the E layer stays and the F layer stays. The layers are formed where the optical depth is equal to 1. And here we have the curve showing the production rate that's given by this equation, where N is the neutral density, sigma I is the ionization cross-section, and phi lambda is the radiation intensity. So we have the radiation intensity here. This is the neutral density. They cross in this point, and this is where we have the maximum production rate. The ion and electron density are balanced between the ionization rate, the production and loss chemical reactions, and transport processes. So there are three things happening: ionization, chemistry, and transport. All these things have an impact on the electron density, the ion density, and the layer structure of the ionosphere. At night, the solar ionization is gone, as I mentioned, and we have these recombinations going on. The density of the plasma is strongly reduced in lower altitudes, and the F region is maintained by transport processes that take the layer upwards towards the F2 peak, where there is a lower recombination happening. Here we can see the vertical profiles of the density of several ionized species that are produced due to these interactions that I just mentioned. So there is a lot of movement within the ionospheric plasma. Transport is an important parameter, and it's governed by three main agents. The neutral winds, which is movement of the neutral atmosphere, and they drag along the ions, and therefore the electrons follow in the proper direction, of course. The electric fields that are created and the fusion processes that happen. So neutral winds arise due to pressure gradient generated by solar heating. That's the main driver. The electric fields are produced by the winds, and they originate in a region, in the E region during the daytime and the F region during nighttime. The diffusion processes happen due to the ionospheric dynamos. So these are complex movement structures that happen in the E and in the F region. So the general mechanism of a dynamo starts with the neutral wind moving the ions via collision. So the neutral part of the plasma move, and they collide with the ions, and they move the ions, and the electrons follow in the opposite direction. There is a plasma motion in the presence of the Earth magnetic field. This induces an electromotive force, and that results in a current, especially in regions where there is a strong conductivity. Due to variations in the horizontal and vertical conductivities, they are not homogeneous. The current and the current density cannot flow freely in any direction, and that creates charge polarization, which creates an electric field, and it changes the current flow again. So this electric field get mapped between the ionospheric regions via the Earth magnetic field lines. So it's a fairly complex process. The dynamos in the dynamo in the E region, in the F region. So we can see a little bit more about the drifts here. So there is a V cross B drift that pushes the plasma up in the F region. Eventually, this plasma comes back down following magnetic field lines, and they close the current loop in the E region. And at night, there is a reversal, and this whole thing moves in the westwards direction. And at night, the wind reverses direction, and the drifts, the plasma drifts towards east then, and it comes down. So the three main currents in the ionosphere are the parallel current. It flows parallel to the magnetic field of the Earth. The Pedersen current, it flows perpendicular to the magnetic field of the Earth, but parallel to an electric field. And the Hall current flows perpendicular both to the magnetic field and any electric field that may be around. So these are the three main currents in the ionosphere. And then we discussed a little bit to what I mentioned before, the Appleton anomaly, which is an anomaly in the ionization of the plasma in the ionosphere. So the ionospheric density changes with latitude. So we see here this little diagram showing how what's going on here that creates this anomaly. The plasma has a maximum density around the 15 degrees north and south, more or less, anywhere on the Earth in the day side. So what happens here, there is this electric field towards the east, so it's coming into the screen here, and in the presence of magnetic field pointing towards the north direction, it creates a plasma drift, and it brings the plasma upward. The plasma, due to the gravity force, eventually will come back down, but it will follow the magnetic field lines, and then it will accumulate in these regions. And then after the accumulation reaches a certain intensity, there are meridional winds that change the density distribution as well. So it looks like this. So here's the magnetic equator, and we also have the equatorial electrojet represented here. The plasma flows upwards and it moves down following the field lines, and more or less around 15 degrees. It varies a little. Many factors change the location, but 15 degrees magnetic latitude, that's an important thing to have in mind. We have this higher density in the ionospheric plasma. So again, we have a very nice movie here from NASA showing how the Appleton anomaly is formed and follows daylight at altitudes of 100 kilometers, showing oxygen emissions. So these are the field lines. We see the sun coming and lighting up the ionosphere, and we see the Appleton anomaly forming here and following this whole region. And as the sun moves, the anomaly moves with it. You can see that it follows the magnetic equator. Therefore, it's not aligned with the geographic equator. And with this perspective, we can see the plasma accumulation in these regions here. So here it is. So this is what I had to share with you all for today. I would like to acknowledge all my colleagues who greatly contributed to this talk, providing slides, pictures, discussions. Inês Batista from INPE, Jonas Souza from INPE, José Leonardo Ferreira from University of Brasilia, and Ramon Lopez from University of Texas, Arlington, in alphabetical order. And thank you very much for your attention. I'm open to answer some questions. I hope I can answer some questions. This is not really my field of expertise. It couples nicely with my field of expertise, which is the new component of the space weather that I was mentioning to all of you before, which is what I'm going to be talking about on Thursday.
Thank you very much for this very nice overview lecture. And yeah, we have time for some questions. If someone has questions, I don't see any in the chat or any in the Slack channel yet, but whoever has a question, feel free to go ahead and ask. Hannah has a question.
Hi, that was really interesting and something very different from what I usually study. My question is, what do you think is like the upcoming research in this area? What still needs to be discovered? Yeah, just be interesting to hear your thoughts on that.
Well, as I mentioned, this is not my cup of tea, so it's not so simple for me to give a perspective, but I know, for example, that the bow shock current is not very well known. Very few people have studied that. So that's one aspect. Of course, everything that has to do with how the energy is making its way back to space is fairly new. There's a lot to be discovered there, how this contributes to space weather if the contribution, how significant the contributions are, how significant the contributions are to human safety on board airplanes, on board space vehicles. The same goes for when we have magnetic storms, substorms. We do know that there is a high increase in radiation, but those things, I don't know how closely it has been studied, the impact on human beings, impact on living beings, for example. We do know that the trees, they hold information on magnetic field changes along many years. There are some colleagues studying the tree rings, and so there is a lot to be studied. All these connections between the different currents. I just mentioned the very basic currents, but when there are magnetic storms, substorms, all these currents get coupled and they change. So there is a lot of dynamics going on there.
Great, thanks.
We have a question in the chat. Sovan, do you want to ask the question directly, or shall I read it out?
Yeah, hi. Yeah, hi. Hi. Yeah, so I was keen to know about some little more about the viscous circulation. So in the sunward, so in the night side of the magnetosphere, so it is in away from the sun direction. Now, how the circulation pattern is forming? So that's why that was my question.
Okay. Let's see.
And even Earth atmosphere also, we have seen such kind of circulation.
Where is it? Here.
Yes.
Yeah, so in a way, it's similar to the main mechanism, which is the Dungeon cycle, because it's transferring the stress that's coming from the solar wind into the magnetosphere. It's coming across the magnetopause, but the way that the currents flow is different. So here, the currents, they are going to flow, creating this circulation patterns in the northern hemisphere and in the southern hemisphere. And these circulation patterns themselves, they are going to induce field-aligned currents that are going to have an impact in the ionosphere, and they are going to create circulation patterns here in the ionosphere themselves. So they create certain types of convection here. And I'm afraid this is as much as I can explain to you about this. If there is anybody here who is an expert in the magnetospheric currents and would like to give us a little bit more information, I'm happy to hear.
Okay, no problem. I will, yeah, that is helpful, really.
So you can take a look at this paper here.
Yeah, I will.
It has a full reference.
Yes. Sure. Okay, thank you.
You're welcome.
Thank you. Are there further questions? No more questions at the moment.
Okay, no problem.
Can you show again the source of that? I just missed it.
Yes, I can. Actually, I can copy and put it in the chat. How does it work?
I think that would work.
Okay, I have noted down. No problem. I will give it. Okay, thank you.
You're welcome.
Any other questions for the moment? Well, perhaps, Elia, you'll also be available sometime in the GADA. If you can tell Barbara some
Sure.
time and we can announce it. And then whenever questions come up later on.
Sure. Sounds good.
Can I ask few more questions? I have one more question.
Sure, go
So
ahead.
in some, I think in the ring current or in the magnetospheric current, there was a eastward current and westward current. So, and the magnitude was different. So I was thinking how this current density becoming divergence less.
Okay, let's go there. Here. Okay, so what is the question?
Yes. So yeah, so eastward current and westward current, how it is getting completed here?
Yeah, so this arises because the pressure it's not homogeneous, it's not isotropic here in the plasma. There is a peak in the pressure of the plasma here. Plasma accumulates here, so this creates a pressure gradient, and this pressure gradient is negative and points towards the Earth in this side, and it points outside the Earth on this side. So because of this B cross gradient of the pressure current density, we can calculate the current, then we're going to have this ring current that actually flows eastward inside
where it
the
is
pressure
generating
peak.
this pressure gradient, where it is creating in the Van Allen region.
I'm sorry, can you repeat?
Yeah, so where it is creating this pressure gradient in the Van Allen region or the ring current?
What is creating the gradient in the plasma pressure?
Okay.
That's a good question. I don't have the answer for you right now, but I can look it up and get back to you later.
Okay. Yeah. Okay. Thank you. Yeah.
You're welcome.
Any more questions? Well, it doesn't seem to be the case for the moment. Perhaps everyone is tired after so much sitting in front of the screen. But anyway.
That's okay.
So
I'll be around in the gather area, and I'm sure that if you guys don't have questions for today, you're going to have a lot of questions for Thursday.
So too, yes. Yeah, thank you very much again. The lectures will continue tomorrow at 2 p.m. Indian time. And meanwhile, I hope you'll all make good use of the GADA space, that you can interact there or play around more with the Jupyter notebooks and all of that. Okay. Then enjoy the rest of the day, everyone. Well, and thanks especially to those joining at very inconvenient times of the day.
All right. Well, see you guys later.
Thank you.
See you.